Welcome back to G Fun Facts Online. Today, we are heading upward, ascending into the thin air of the world's highest mountain ranges. In our collective imagination, mountains are the planet's eternal freezers. We see them as immutable bastions of rock and ice, standing apart from the frenetic changes of the lowlands. We picture the Himalayas, the Andes, and the Alps as cool sanctuaries, immune to the heat that bakes our cities and plains. But science tells us that this image is now a relic of the past. A quiet, invisible crisis is unfolding above the tree line. The world's highest elevations are not merely victims of global warming. They are its amplifiers. This phenomenon is known to scientists as elevation-dependent warming, or, more colloquially, elevation amplification. It describes a startling trend where high-altitude regions warm significantly faster than the global average, in some cases, up to twice as fast. While the Arctic and its melting sea ice grab the headlines, the vertical amplification happening on our continents is equally drastic, but far less understood. From the thinning air of the Tibetan Plateau to the vanishing snows of the Rockies, elevation amplification is reshaping the planet's hydrology, biology, and geography. It is a story of physics and feedback loops, but it is also a human story involving farmers in Peru, engineers in Ladakh, and ski resort operators in Switzerland fighting to adapt to a world that is literally melting beneath their feet. To understand why mountains are warming faster than the rest of the planet, we have to look at the unique atmospheric physics that govern high altitudes. The warming we experience at sea level is primarily driven by the greenhouse effect, but as we ascend, secondary mechanisms kick in that supercharge this process. The most potent driver is the snow-albedo feedback loop. Albedo refers to the reflectivity of a surface. Fresh snow is one of the most reflective surfaces on Earth, bouncing up to 90% of incoming solar radiation back into space. In contrast, bare rock, dark soil, and alpine vegetation absorb most of that energy. As global temperatures rise, the snow line, which is the elevation where snow remains year-round, creeps upward. When snow melts earlier in the spring, or fails to cover the ground in winter, it exposes the darker surface beneath. This dark surface absorbs sunlight, heats up, and radiates that heat into the immediate atmosphere, which melts even more snow, exposing more dark ground. In the lowlands, this effect is minimal because snow cover is transient. But in mountain ranges, where snow cover defines the landscape for months or years, the loss of reflectivity creates a massive local heat source. This is why the rate of warming often peaks just around the freezing level, the 0 degrees Celsius isotherm, where snow cover is most sensitive to slight temperature nudges. Then there is the water vapor feedback. The atmosphere at high altitudes is naturally thinner and drier than at sea level. In humid tropics or low-lying plains, the air is already saturated with water vapor, which acts as a potent greenhouse gas. Adding a little more heat there doesn't drastically change the greenhouse capacity of already soupy air. However, in the cold, dry air of the high mountains, water vapor is scarce. As these regions warm, the capacity of the air to hold moisture increases. According to the Clausius-Clapeyron relation, air can hold about 7% more moisture for every degree Celsius of warming. When more water vapor enters this previously dry high-altitude air, it traps outgoing heat much more effectively than it would at sea level. This creates a disproportionately strong greenhouse effect specific to high elevations. Pollution also plays a surprisingly complex role in this warming through what is called the elevated heat pump effect. In regions like the Himalayas, which sit downwind from the massive industrial and agricultural emissions of the Indo-Gangetic Plain, clouds of brown haze rise against the mountain face. These aerosols, composed of soot, dust, and sulfates, absorb solar radiation. Instead of the sun heating the ground, these particles heat the air column itself at specific altitudes. This warms the mid-troposphere, accelerating the melting of glaciers, even when surface air temperatures might suggest otherwise. Furthermore, when black carbon or soot settles on pristine white glaciers, it darkens the ice, reducing albedo and accelerating melt directly. Even clouds are changing. In many mountain regions, climate change is altering cloud patterns. If cloud cover increases at night, it acts like a blanket, preventing the mountain surface from cooling down. Conversely, a decrease in daytime clouds in summer can increase the amount of direct solar radiation striking the peaks. The complex interplay of shifting cloud bases means that some elevations are constantly being insulated more than before, trapping heat that used to escape into space. Let's take a tour of the roof of the world to see how this plays out, starting with the Himalayas. The Hindu Kush Himalaya region is often called the third pole because it holds the largest reserve of frozen water outside the Arctic and Antarctica. It is the water tower for Asia, feeding 10 major river systems, including the Indus, Ganges, Brahmaputra, and Mekong. Over 1.9 billion people depend on these waters. Recent data indicates the Himalayas are warming at a rate of roughly 0.3 to 0.7 degrees Celsius per decade, which is significantly faster than the global average. A 2025 study led by researchers at the University of Portsmouth confirmed that this region is warming nearly 50% faster than the Northern Hemisphere average. One of the most terrifying consequences of this is the threat of glacial lake outburst floods, or GLOFs. As glaciers retreat, they leave behind massive depressions, often blocked by moraines, which are unstable piles of boulders and dirt. Meltwater fills these depressions, forming high-altitude lakes. When the moraine dam fails due to an avalanche or simple pressure, it releases a catastrophic wall of water. In October 2023, the South Ladakh Lake in Sikkim, India, burst its banks. A torrential flood cascaded down the Teesta River, destroying the Chungthang Dam and claiming over 70 lives. This was not a freak accident. It was a predicted consequence of elevation amplification. Sikkim has since become a pioneer in mitigation, installing early warning systems with sensors that detect sudden drops in lake levels to trigger sirens in villages downstream. However, people are also adapting in ingenious ways. In the high-altitude desert of Ladakh, India, water scarcity is an existential threat. Glaciers have retreated so far up the mountains that spring meltwater no longer arrives in time for the sowing season. Enter Sonam Wangchuk, a Ladakhi engineer who reinvented the concept of artificial glaciers. Wangchuk devised the ice stupa, a conical heap of ice created by piping winter stream water down vertical pipes. Gravity sprays the water into the freezing night air, where it freezes on a structure of brushwood. The conical shape minimizes the surface area exposed to the sun, allowing the ice to last well into late spring. When it melts, it provides critical irrigation water just as farmers need to plant their barley and peas. Some of these stupas tower over 100 feet, a striking example of grassroots adaptation. Moving to South America, the tropical Andes of Peru, Bolivia, Ecuador, and Colombia are home to 99% of the world's tropical glaciers. These ice masses are particularly sensitive because the temperature remains close to the melting point year-round. A 2025 study published in Science used cosmogenic isotope analysis to determine that Andean glaciers are now smaller than they have been at any point in the last 11,700 years. They are losing mass up to 10 times faster than the long-term historical average. The impact here has moved from the mountains to the courtroom. Saul Luciano Lioya, a farmer from Huaraz, Peru, lives beneath Lake Palcacocha, which has swollen dangerously due to glacial melt. In a landmark case, Lioya sued the German energy giant RWE. His argument was novel but scientifically grounded. He argued that RWE, as a major historic emitter, contributed roughly 0.47% to global emissions. Therefore, they should pay 0.47% of the cost of engineering works needed to secure the lake. The case has proceeded through German courts, relying heavily on the science of attribution. Meanwhile, agricultural migration is underway. In the Peruvian highlands, farmers who used to plant potatoes at 3,800 meters are now pushing their fields to 4,000 meters or higher to find the cool temperatures the tubers need. But this upslope migration has a hard ceiling, the mountain peak. Once they reach the top, there is nowhere left to go. In Europe, the Alps are the most densely populated and instrumented mountain range in the world, and here the impacts are visible in the collapse of physical infrastructure. Mountains are held together by permafrost, ice that acts as cement within the cracks of rock faces. As the Alps warm at roughly twice the global rate, this glue is melting. The result is an increase in rockfalls that threaten hikers and villages. The iconic Matterhorn has seen closures to climbers in recent summers due to instability. Ski resorts are fighting a losing battle, turning to snow farming, which involves covering massive piles of snow with sawdust or reflective fleece blankets over the summer to preserve them. But perhaps the most poignant shift is biological. The Alpine Ibex, a species of wild goat, is becoming a climate refugee in its own home. Researchers found that ibex are shifting their behavior from being active in the day to being nocturnal, to avoid the heat stress of the midday sun. This shift makes them more vulnerable to predators like wolves, which hunt effectively at night. In the North American Rockies, elevation amplification is threatening the delicate balance of the Colorado River Basin, which supplies water to 40 million people. Warming here doesn't just mean less snow, it means wetter snow and earlier melt. The snow-water equivalent is declining, and more precipitation is falling as rain rather than snow. This hydrological mismatch contributes to the megadrought conditions seen in the American Southwest. The ecological toll is visible in the plight of the American pika. This small relative of the rabbit lives in high-altitude boulder fields and is physiologically incapable of surviving high heat. Temperatures above 78 degrees Fahrenheit can be lethal to them. As the Rockies warm, pikas are experiencing range contraction. Their lower elevation populations are dying out, and they are moving higher. Researchers predict pikas could be extirpated from Rocky Mountain National Park by the year 2100 if warming continues. They are the canary in the coal mine for the alpine ecosystem. This forces us to confront the ecological cascade known as the escalator to extinction. As temperatures rise, species move upslope to remain in their thermal comfort zone. Lowland species move into the foothills, subalpine species invade the alpine meadows, and alpine specialists are pushed to the very summits. The problem is geometry. Mountains are shaped like pyramids. There is less surface area the higher you go. As species move up, they are squeezed into smaller and smaller islands of habitat. The Global Observation Research Initiative in Alpine Environments, or GLORIA, confirms that while plant species richness on summits is temporarily increasing as lowland plants move up, it comes at the cost of specialized cold-adapted plants, which are being outcompeted. We are witnessing a homogenization of mountain flora. Furthermore, there is the carbon sink paradox. The Tibetan Plateau has long acted as a carbon sink, but permafrost thaw is the wildcard. As frozen ground melts, it allows microbes to decompose ancient organic matter, releasing methane and carbon dioxide. If the Tibetan Plateau flips from a sink to a source, it could trigger a runaway feedback loop. Ultimately, the most terrifying implication of elevation amplification is the disruption of the hydrological cycle. Mountains are the world's water towers. In the short term, rapid glacial melt leads to an excess of water and floods. But once the peak water point is passed, which has already happened for some Andean and Himalayan glaciers, the water supply will terminally decline. For a farmer in the Indus Basin or a city planner in Lima, the reliable flow of glacial meltwater will be replaced by erratic rain-fed flows, threatening food security for hundreds of millions. Culturally, for indigenous communities, the loss of snow and ice is a spiritual abandonment. Pilgrimage routes are becoming dangerous, and sacred lakes are disappearing. So where do we go from here? Adaptation is no longer theoretical. It is a survival mechanism. We are seeing the expansion of early warning systems for floods and engineering projects to lower glacial lake levels. In agriculture, communities are reintroducing ancient resilient crop varieties and turning to efficient water harvesting. But the trajectory of elevation amplification depends entirely on global emissions. In a low-emission scenario, we might stabilize warming and save a portion of the ice. In a business-as-usual scenario, we face the total loss of tropical glaciers and up to 2/3 of Himalayan ice by 2100. Elevation amplification is a warning siren sounding from the highest points on Earth. It tells us that the planet is more sensitive than we thought. What happens at 5,000 meters does not stay at 5,000 meters. The water that melts there feeds the grain that feeds the world. The heat that radiates there changes the jet streams that steer our weather. Preserving these high places requires immediate, hyper-local adaptation and a global push to decarbonize. We cannot refreeze the glaciers overnight, but by slowing the ascent of the thermometer, we might give the mountains, and the billions who depend on them, a fighting chance. Thanks for listening to Fun Facts Online.